Hello everyone, my name is Adnane Khattabi and today I'll be presenting the joint work with Hendler, Alessia, Milani and Corentin Travers titled Upper and Lower Bounds for Deterministic Approximate Objects. First, I'm going to start with some context. Linearizable shared objects such as the counter and max register are fundamental building blocks for distributed algorithms. However, it has been shown in numerous work that the implementation of these objects is expensive. So in order to remedy the cost, it's been proposed recently to relax their semantics in order to improve the complexity of their implementations. So we were interested in studying the relaxation of the sequential specification of different objects and how it affects their complexity. More specifically, we were interested in max register and counter objects, but for the sake of this presentation, I'm going to focus on the counter. So a counter object is defined by the two operations of counter increment and counter read. A counter increment increases the value of the counter by 1, and a counter read returns the number of previous calls to counter increment. When relaxing the exact counter into a K-multiplicative-accurate counter, the definition of a counter increment operation remains the same, and the relaxed counter read operation returns a value within a margin of error of a K-multiplicative factor from the value returned by the exact counter. So we are looking to implement the K-multiplicative-accurate counter in a shared memory model with n asynchronous deterministic processes that are prone to crashing and that communicate with each other using read, write, and test and set primitives. The correctness condition considered is linearizability, which basically ensures that any concurrent execution of high-level operations, which in the case of a counter are counter increment and counter read, is equivalent to a sequential execution where all the high-level operations appear to take effect instantly and behave according to the sequential specification of the object. Next, we have a table that summarizes the state of the art for the exact counter. So we have a worst-case step complexity lower bound of omega n given by Gianti et al. And a matching upper bound given by Inoue et al. It also has been shown that when considering bounded executions of the exact counter, it is possible to beat this lower bound, and Asmus et al. Have given an implementation that is polylogarithmic. Finally, Baig et al. Have given an implementation of the exact counter that has an amortized step complexity of log square n. So to reiterate, we are looking to study the relaxation of the sequential specification of the counter object and how it affects its complexity. So in this regard, our contributions are as follows. We present the first deterministic weight-free read, write, and test and set based K-multiplicative-accurate counter that has a constant amortized step complexity when the approximation parameter K is greater or equal to the square root of n. Then, by extension to the result by Atiyah and Hendler, we prove a lower bound on the amortized step complexity of log n over k squared when the approximation parameter is lower or equal to the square root of n over 2. And finally, we prove that the worst-case step complexity lower bound given by Gianti et al. For the exact counter holds for unbounded K-multiplicative counters as well. The intuition behind the implementation of the K-multiplicative-accurate counter is to represent the counter value v in a k-base and using the index of the most significant bit in this representation to approximate the value of the counter within a range defined by the sequential specification of the object. More specifically, the shared counter is an infinite array of bits, and each process has two local variables, a local counter and a threshold initialized to 0 and 1. When the process first calls the counter increment operation, it increases the value of the local counter to 1, and since it reaches the value of the threshold, it writes the value of the first bit in the shared counter using a test and set primitive. When the test and set succeeds, the process resets the value of the local counter to 0 and updates the value of the threshold by multiplying it by a factor of k. After the first bit, the shared counter array is segmented into sets of k bits with the common characteristic that all the bits in the same set require the same number of counter increment calls to be written by a process. So after the first bit, the process will need k separate counter increment calls before attempting to write a bit in the first set. And this will continue until there are no longer any available bits in the set, and only at that point will the process update the threshold once again by multiplying it by a factor of k. And since multiple processes can execute counter-increment operations concurrently, it is possible that the value of the threshold stored by a process becomes obsolete. And when that happens, a process with an old value of threshold will attempt to write a bit in a set where no longer any available bits exist. And at that point, the process will keep the value of the local counter the same and only update the value of the threshold by a factor of k at a time. And this continues until the process reaches the most recent set, and at that point, it will be able to write a bit and reset the value of its local counter. When a process calls a counter read operation, it searches for the first bit that has not been written by a process yet. We proved that a process only needs to check the first and last bits of each set in order to approximate the value of the counter within the range defined by the sequential specification of the K-multiplicative-accurate counter. So to summarize, we've given an implementation of the K-multiplicative-accurate counter that has a constant amortized step complexity when the approximation parameter k is greater or equal to the square root of n. And we've also given a lower bound on the amortized step complexity of log n over k squared when this approximation parameter is lower or equal to the square root of n over 2, meaning that in this case, it is only possible at most to gain a logarithmic factor. We've also shown that the lower bound on the worst case step complexity given by Jayanti et al. For the exact counter holds for the case of the K-multiplicative-accurate counter as well. As a final thought, this has been a first step in trying to understand how the relaxation of the sequential specification affects the complexity of linearizable concurrent objects implementations, and we'll be interested in the future in studying different kinds of objects in order to understand what characteristics influence whether or not we benefit from the relaxation. Thank you for your attention, and I'd be happy to answer any questions you may have.